Hello grade 10s and welcome to SOS Science. This channel will follow the CAPS Physical Sciences syllabus, and this particular topic is matter and material, and we'll start with the first section of matter and material of the grade 10 syllabus, which is revision of matter and classification. So in this section we are going to revise properties of materials. We are going to describe matter as being made up of particles, as we did in grade 8 when we learned about the particle model of matter. We are going to differentiate between atoms, elements, molecules, and compounds. We'll define pure substances, mixtures, and then we'll define homogeneous and heterogeneous mixtures. We are going to illustrate the microscopic representation of materials. We will classify substances as metals, nonmetals, and semimetals or metalloids, and we'll identify their positions on the periodic table. And we will learn how to write names and formulas of elements and compounds. Most of this chapter is really revision of things that you've covered in grade 7, 8, and 9. So different materials have different properties, and properties of materials are the characteristics that make materials unique. So you might choose a raincoat because it has a special characteristic of being waterproof. You might choose to build a home out of bricks because bricks are strong. So there are several properties of materials that we need to be familiar with, and we need to know what they mean. So a material might be strong or weak. A strong material can withstand a lot of force or a lot of pressure, and a weak material cannot. Then we have materials that are flexible and materials that are rigid. And so the more flexible a material, the more bendable it is. Absorbent versus waterproof. An absorbent material allows liquids to be soaked up into it, and a waterproof material does not. Now, when we talk about brittle, malleable, and ductile, we have to be really aware of the fact that the word brittle applies to nonmetals. So here we've got a piece of coal, and if you hammer a piece of coal, it is just going to crack into lots of little pieces, and that's what it means that it is brittle. Malleable and ductile are words used to describe only metals. A malleable material can be hammered into shape and it won't crack. And a ductile material can be drawn out into a thin wire. So again, malleable and ductile applies to metals. Brittle will apply to nonmetals. This piece of coal cannot be hammered without cracking, and it cannot be drawn out into thin wires. Another important property is whether a material is an electrical conductor or an electrical insulator. An electrical conductor allows electric current to flow through it, whereas an electrical insulator, something like glass or plastic, will not allow an electrical current to flow through it. Now, what we need to understand is that we get conductors of electricity that are good, like copper and gold and silver, but then we also get conductors of electricity that are poor conductors of electricity. So we get certain metals that don't conduct electricity very well. So they're still known as electrical conductors. They're just poor electrical conductors. A material that is an electrical insulator cannot allow current to flow through it at all. So materials like copper and aluminium are good electrical conductors, so we use that in our wiring, but we cover our wiring in an insulator like plastic so that we don't get electrocuted. Now, we also get thermal conductors and insulators, or heat conductors and insulators. So be very careful when you refer to a material as an insulator or as a conductor. Make sure that you specify, are you talking about a heat conductor or an electrical conductor? Are you talking about a heat insulator or an electrical insulator? So a thermal or heat conductor allows heat to flow through it easily. So that means that the heat flows into the material easily, but it also flows out of the material easily. So if you're going to heat up food or water or soup in a pot, well, the material that the pot's made of is a wonderful thermal conductor. So it will absorb the heat from the stovetop. It will absorb it into the metal, and then it will cook your food. However, once this heat is turned off, that heat will also be lost quite quickly and quite easily, because again, a heat conductor doesn't only allow heat into it easily, it also allows heat to flow out of it easily, as opposed to a thermal or heat insulator, which is a poor conductor of heat energy. So if you think about the bricks around a swimming pool, in the morning, even when the sun's shining, they're going to feel quite cool. And as the day progresses, the bricks slowly absorb that heat energy, and eventually they do get quite hot. But what you would notice is that by 5 or 6 o'clock, when the sun's gone down, those bricks around the pool are still warm, and they remain warm for quite some time. That's because that is a thermal insulator, meaning that it doesn't allow heat energy to flow into it easily, but then it also doesn't allow heat energy to flow out of it easily. So materials like stainless steel and aluminium are good heat conductors, so we use them to make pots and to heat our food in those pots. But the handle is made up of a heat insulator so that we don't burn our hands. Now, a heat insulator is not a material that doesn't allow heat to travel through it at all. It just makes it difficult. So be very careful, because an electrical insulator doesn't allow electricity to travel through it at all. Then we get magnetic versus non-magnetic materials. So magnetic materials have a magnetic field that surrounds them. Now, most metals can be magnetized, they can be temporarily magnetized, they can be weak magnets, but we have 3 metals that are permanent magnets, meaning that once they've been magnetized, they will remain magnets forever. They don't lose their magnetism. And those elements include iron, cobalt, and nickel. So other metals, like I said, can also be magnetized, but that would not be a permanent magnetic field that would be created around them. So how do we magnetize a metal? Well, either we have to put it in the presence of a permanent magnet. We can rub it with a permanent magnet as well. But another very important way, and we need to be aware of this, especially when we get to the grade 11 syllabus, is that when we pass an electric current through a metal, so here we've got a piece of metal with an electric current flowing through it, and what we can see is that a magnetic field gets created. Now, the moment that that current stops flowing through this wire, the magnetic field will disappear. So that actually has a very specific name, and that's called an electromagnet. An electromagnet is a metal that has an electric current flowing through it, and that is what produces that magnetic field around it. So what you're seeing here is just tiny little pieces of iron filings, and those iron filings, because they're so small and so light and they're magnetic, they align with the magnetic field lines around this conducting wire. Now, different materials have different melting and boiling points, right? So each material has its own unique melting and boiling points. Now, what we need to know is when a material melts or boils, the chemical composition of the material remains the same. So it doesn't change chemically. It is only the state of the material that changes, and a change of state involves the distance between the particles and the forces of attraction between the particles, but we're going to discuss that a little bit later in the section. Some materials don't have the ability to melt or boil, but they burn in the presence of heat. So anything that is carbon-based, all living things, they are not able to melt. That is called burning, but burning is not a change of state. Burning is a decomposition chemical reaction. So it's a chemical reaction, specifically a decomposition chemical reaction. So if you recall, a decomposition chemical reaction is when chemical bonds are broken. A synthesis chemical reaction is when chemical bonds are formed between atoms. Another very important property of materials is the material's phase or state at room temperature. So the words phase and state may be used interchangeably. So when we want to know the phase or the state of a substance, automatically it means at room temperature unless otherwise specified. So here we want to know, is the substance a solid, a liquid, or a gas at room temperature? And when we talk about room temperature, you need to be aware of this. We are talking around 20 to 23 degrees Celsius. Now, density is another very important property of materials, and different materials have different densities. Density is calculated as mass divided by volume, which is why density is defined as the mass per unit volume. So the mass is how many particles there are. How many particles makes up a certain substance, and the volume is, well, how much space do those particles fit into. So you may think of density as how closely together the particles are arranged. The more mass that you can fit into a certain space, well, the more closely together the particles will be arranged, and therefore the higher the density will be. If the particles that make up a material are arranged very closely, that means that we can fit more mass into this given space, which means that this substance over here has a higher density than this one over here, where into the same amount of space we can fit in fewer particles, and this substance over here has a medium density relative to the other two. Now, there are other properties of materials. Some materials are more durable than others. Some are rust-proof, some are shiny, some are matte, elastic, inelastic, fibrous, easy to clean, cost-effective. So there are many, many properties of materials that we need to take into account when we choose a material to provide us with a certain function. Now that we've revised materials and their properties, we can move on to the particle nature of matter. So we say that all matter consists of particles, but what are particles? Well, when we talk about a particle, we're not specifying, but we might be referring to an atom or an element or a molecule or a compound. So referring to a particle really just makes it easier for us to communicate, because we don't need to differentiate exactly what those particles are made of. It's not always useful, but in many instances, it is useful to just discuss particles. Now, wherever you see this little d over here, that means that it is a definition, and definitions need to be learned off by heart, word for word. What my students do is, as we go along through our workbook, they have a separate list of definitions next to them, and they write in every single definition as we go along, so that when it comes to studying for the test or the exam, it's all in front of them. So what is an atom? An atom is the most basic single particle that makes up matter. So, for example, here we have a lithium atom, and a lithium atom is made up of 3 protons, 3 electrons, and then those green things are the neutrons that live in the nucleus with the protons. So this would be an example of a lithium atom. Now, most substances in the world chemically react and bond together to form molecules or compounds. Very few substances exist as unattached atoms, and we're going to understand later on in the section why that is. It is generally only noble gases, which are group 18 elements, that remain as unattached atoms. Noble gases never ever chemically react. They're unreactive, and we need to know that noble gases may also be referred to as inert gases. So we'll come back to noble gases a little bit later, and we're going to understand why noble gases don't react. That brings us to the next definition of an element. And an element may be defined as a pure substance that consists of only one type of atom. Now, what does that mean? So we know that the periodic table of elements represents all the elements known to us. Now, in the previous slide, we saw a single lithium atom made up of 3 protons, 3 electrons, and 4 neutrons. And so that is a single lithium atom. And a single lithium atom is obviously going to be made up of the element lithium. That's simple. But now we've got chunks of lithium metal, and this is made up of millions and millions and millions of lithium atoms. But we can also say that this is made up of the element lithium. So because it is only made up of one type of element, we can refer to this in singular form. So now the definition makes a bit more sense. It is a pure substance that consists of only one type of atom. Whether it is a single atom or millions and millions of atoms, we still refer to it as the element lithium, singular. Now, this brings us to the definition of a molecule versus a compound. A molecule is a substance that is made up of more than one atom chemically bonded, whereas a compound is a substance that is made up of more than one type of atom chemically bonded. It might seem like a subtle difference as far as the definition is concerned, but it actually has big implications in chemistry. So if I give you a substance like oxygen gas, which is a diatomic molecule, or ozone, which makes up the ozone layer, which is a triatomic molecule. So oxygen gas is 2 oxygen atoms chemically bonded to each other. The ozone layer is made up of O3, which is 3 oxygen atoms chemically bonded to each other. Now, does this fit the definition of a molecule? Let's see. More than one atom chemically bonded. Well, yes, here we've got 2 atoms chemically bonded, and here we've got 3 atoms chemically bonded. So yes, it fits the definition of a molecule. Does it fit the definition of a compound? Well, a compound is a substance made up of more than one type of atom, but I've only got one type of atom here. I've only got one type of atom here. It's only oxygen involved. So that means that O2 and O3 are molecules, but O2 and O3 are not compounds. let's take into account H2O, which is water, or CO2, which is carbon dioxide. Now let's take a look at the definitions. A molecule is more than one atom chemically bonded. Is H2O made up of more than one atom chemically bonded? Yes. And CO2? Yes. So these are both molecules. Now, a compound is a substance made up of more than one type of atom chemically bonded. Is this a compound? Yes, because we've got hydrogen and oxygen. We have at least two different types of atoms involved in this bond. And over here, also we've got carbon and oxygen. So that means that H2O and CO2 are both a molecule and a compound. These guys over here are molecules, but not compounds. So what does that mean? Well, it means that not all molecules are compounds, but all compounds are molecules. This is a nice video that might help you to understand or recap the whole idea of elements, atoms, molecules, and compounds. And then this brings us to a small exercise. I would like you to consider the following substances and classify each one of them as a molecule or a molecule and a compound by filling in the table below. So I'd like you to pause the video now and try to do this on your own. So I'll start you off. S8. Is S8 only a molecule, or is it a molecule and a compound? Well, S8 fits the definition of a molecule because it is made up of more than one atom that is chemically bonded. But does it fit the definition of a compound? No, it doesn't, because it is only made up of one type of atom that's chemically bonded. And to be a compound, you need at least two types of atoms that are chemically bonded to each other. So S8 would be only a molecule. I would like you to pause the video now and complete the table on your own, and then you can resume the video and go through the answers with me. O3 is made up of only one type of atom, therefore it is only a molecule. CO2 is made up of carbon and oxygen, so it is both a molecule and a compound. O2 is only a molecule. NaCl is a molecule and a compound. I2 is only a molecule. CaSO4 is a molecule and a compound. P4 is only a molecule. And then all the rest, NH3, CH4, and Fe2O3, are a molecule and a compound because all of them are chemically bonded and they are made up of at least two different types of atoms. So NH3, CH4, and Fe2O3 all belong in this column. Now, the atoms that make up molecules are always combined in a fixed ratio. So what we mean by that is that if a water molecule is H2O, then that means that water is always made up of how many hydrogen atoms and how many oxygen atoms? Well, it's two hydrogen atoms and one oxygen atom. Note that when there's no subscript number, that automatically means 1. So the ratio of hydrogen to oxygen in any water molecule will always be 2 to 1. Now, if water and oxygen instead combined in a 2 to 2 ratio, what molecule would that form? Would that form water? Absolutely not. It would form H2O2, which is hydrogen peroxide. It is a bleaching agent, and it has a completely different set of properties to H2O. So what we need to understand is that for any given molecule, the atoms always combine in a fixed ratio to form that particular molecule. So here we've got a molecule of H2O, and here we've got H2O2, completely different substances.